All right, one more drawing I want to do for you today, and in this drawing, I'm going to show you how we protect linear chromosomes from erosion in prokaryotes. So some prokaryotes have linear chromosomes in addition to their looping chromosomes, or in place of their looping chromosomes. And you hopefully remember from intro bio that this is a problem because we have the end replication problem where Okazaki fragments in their primer sites leave some parts of the telomeric regions exposed, which means the chromosomes, what ends up happening is the chromosomes get shorter and shorter in each round of replication. So in eukaryotes, we can prevent this from happening during in cell lineages that have a lot of cell division by using an enzyme called telomerase. And telomerase can build additional simple sequence repeats onto the ends of the chromosomes, essentially lengthening them. But prokaryotes do not have this type of activity. Prokaryotes, when they have linear chromosomes, they have a way of disguising the telomeres, the ends of our linear chromosomes. So that's what I'm going to draw for you. And the example I'm going to give you here is from a prokaryote near and dear to my heart. Unfortunately, literally, Borrelia burgdorferi. Borrelia burgdorferi is a spirochete that is the causal agent of Lyme disease. Which is a disease that I have been diagnosed with. I did get it treated and it seems to be resolved. One of the symptoms of Lyme disease is atrial fibrillation, which is not great. And when I was first diagnosed, they said, "Oh, you've got AFib." And I'm like, "Oh, doesn't sound good," and it wasn't. But that condition has not been recognized again, so it seems that it's been resolved to me. So when I say it's near and dear to my heart, that's what I mean. But Borrelia burgdorferi is that causal agent, and it has a linear chromosome. Okay, so I'm going to use some colors here to represent that linear chromosome. Okay, so I'm going to use blue and red. And this is somewhat exaggerated because this is a long linear chromosome. So in the middle here, we've got this complementary double-stranded molecule. And in the telomeres, we do have some simple sequence repeats, but which I'll abbreviate as SSR, in the ends of these chromosomes forming what are known as hairpins. So, as you may know from either using hairpins in your own hair or from driving and knowing that a hairpin turn means you've got a tight turnaround. So basically, it's really a loop of DNA, but it's a weird loop because it's not a double-stranded loop. It's a single-stranded loop that has looping bits at the end that are these hairpins. So there's a hairpin here, and there's a hairpin here. Okay, so we have also an ORI site, an origin of replication, just one. And when this molecule is getting replicated, we're going to find some interesting things happen. So we got our hairpins. We're going to open up our replication bubble, going into our replication fork. Okay, and so one of the interesting things that happens at our ORI site is that we only copy the leading strand. So DNA replication begins at ORI site, and only the leading strand is synthesized. Weird, right? Seems like that's kind of breaking some rules that we know about, but you know, this is biology. We kind of gotta get used to that. And so what's going to happen is that we're going to end up with, oops, I went into my arrow there. The whole chromosome is going to get copied over the lines. My dogs are like, why are you talking to yourself so much? Are you okay? I'm fine, Miss Ilio. Fine. Okay. So we have these simple sequence repeats in the telomere regions, which are recognized by an enzyme called REST, which stands for telomere resolvase. Telomere resolvase recognizes the simple sequence repeats in the hairpins, and cuts them and rejoins them. To create new hairpins. So what we end up with, based on the action of REST, is 2 copies of our molecule, each of which is going to have a newly synthesized daughter strand, which is being represented here in the black ink. Because REST comes in and basically snip, snip. Try a little teeny tiny scissor over here, snip, snip. Cuts and pastes it all back together, so we end up with completely replicated linear chromosomes. So I think this is really fascinating and interesting, just showing once again how diverse the toolbox is for prokaryotes and how they solve these kinds of issues.